So we start a course of general physics today, and during this first year I will be your physics instructor, and my name is Aleksey Ilyin. Oh, sorry, this is something. My name is Aleksey Ilyin. I'm an associate professor of physics here at this University of Physics and Technology. And we will discuss different topics of general physics, starting from kinematics. And then in 3 years, you will end with quantum physics. So the course of general physics lasts for 3 years, that is 6 semesters here at this university. The first semester will be devoted to the introduction to physics. The second semester will be devoted to mechanics. And then you will have thermodynamics and molecular physics. And then electricity and magnetism. And then finally, semester number 5 will be optics, and semester number 6 will be atomic physics or quantum physics. So in 3 years, you will study the whole spectrum of issues devoted to general physics. And along with general physics, a few years later, you will start learning theoretical physics, including theoretical mechanics and field theory, etc. And also, by the end of your studies in a bachelor program, you will study some specialized subjects, depending on what specialty you have chosen. But in order to understand the special subjects, you must first of all learn the basics of physics and mathematics, because without the physics and mathematics, it's impossible to learn modern technology and modern science and modern engineering. Physics is very important to understand special subject, very important to understand any engineering field of human activity. Physics studies the most fundamental laws of nature, and therefore physics lays the foundation of any natural science, like chemistry, biophysics, biochemistry, etc., etc. Any engineering or any natural science is based on physics laws. So we start from the simplest laws today, from kinematics. And also, physics is very important to know. Knowing laws of physics is very important to have a correct understanding of nature, correct understanding of natural phenomena, and which you encounter every day. Because people who don't know physics, don't know laws of physics, they are somehow, they probably tend to explain natural phenomena using superstitious and prejudiced commonplace. Come in and sit down. So people who don't know physics laws, they tend to explain natural phenomena using unnatural explanation, so to say, which is certainly incorrect. Physics is important because it allows you to understand nature as a whole and natural phenomena around you, and it lays the foundation of any natural science, any engineering and technical field of activity. It's important to say in the very beginning that there are many laws in physics, but there is no single law which is absolutely correct. Any law in physics is violated in certain situations. It means that any law in physics has a very limited domain of applicability. Most of physics laws are applicable and work very well in a laboratory, in our Earth laboratory. But the situation, the conditions within the Earth laboratory are very simple. We have very small gravitational fields, very small electrical fields and magnetic fields. We have very low temperature, relatively low temperature compared to the temperature in the stars, for example. We have relatively low pressure, again, if compared with pressure inside the planet Earth or inside the stars. So we have very mild conditions in our Earth laboratories. And in these conditions, if we take some simple bodies, they have small mass and they move at small velocity, and therefore the laws of physics which govern the behavior of bodies and the behavior of natural phenomena in our physical laboratory. These laws of physics are simple and they work well in this laboratory, in our laboratories. But if you go to different conditions, then the laws of physics will change. If you go to very high gravitational fields, if you go to very high magnetic fields, into the area of high magnetic field, if you go to very high temperatures, very high pressures, etc., you will see that the laws of physics change. But we don't know how do they change. We know very little about nature. We don't know everything about nature. You have to take this into account. Always you have to remember that any physics law is correct only in certain domain of its applicability. Any physics law is correct only in certain situations, in certain conditions. And if you go beyond these conditions, beyond this border of applicability, the law will become inapplicable. It will give you an error. The law will not work properly. For example, if we take laws of classical mechanics, you know, Newton's laws of dynamics, they work very well in our laboratories on the surface of this planet Earth. But if you choose to observe bodies moving at high velocities close to the velocity of light, you will notice that something is wrong. The laws of Newtonian mechanics do not work properly. They will give you a mistake. They could not be applied to produce a good result. No. They must be changed somehow. If you go to high velocity domain, if you consider movement at high velocities close to the velocity of light, then the laws of classical mechanics must be changed. Well, about 120 years ago, people didn't know how to change the laws of classical mechanics. Only with the works of Albert Einstein, starting from the beginning of the last century, it became clear how to change the laws of classical mechanics when you consider high velocities of movement. And so now we know how to change the laws, how to apply the laws of mechanics to deal with high velocities. We know, but we still don't know everything. there are still many issues which are unknown to science. And so every physics law has a very limited domain of applicability. And you must always be very careful in applying physics laws in order to apply it in its domain of applicability. If you attempt to apply a physics law beyond the domain of applicability, then you will obtain incorrect result. The law will not work. It will produce an error. That's for the beginning. That's very important remark. You should remember, you should know from the very beginning that no physics law is absolutely correct. That is, no physics law is absolutely correct. Every physics law is violated in some situation, in some conditions, somewhere, sometimes. Every physics law is violated. That means that we don't know the whole truth about nature. We don't know the ultimate laws of nature. Nobody knows. That is why, by the way, you can find every day some scientific news about scientific discoveries. Somebody in some laboratory made a discovery. Every day discoveries are made. Every day people discover something new. Somewhere they discovered, for example, a new phenomena at low temperature physics, extremely low temperature physics, low temperature solid state. Somewhere in other laboratory people discover new phenomena at high temperature plasma, etc., etc. Somewhere they discover something new in biophysics. Every day we see the discoveries. Every day somewhere somebody makes a discovery. Why? Because we don't know everything about nature. We know very little. And there are a lot to be discovered. So, okay, after these introductory words, we may start kinematics, but I would like to tell you another thing. So we start from the introduction to physics. This course of introduction to physics is designed to help you understand what must be the level of your knowledge and the level of your skill in order to be a successful student at this university. In this group of foreign students, we have students who came from different countries. And in different countries, the physics syllabus is different. In different countries, students have different level of knowledge. So we must repeat here in this course of Introduction to Physics, we must repeat the basic laws of physics which are usually studied at school. And we must solve physics problems so that you understand how to solve complicated problems. And that is the purpose of this introductory course, Introduction to Physics. The purpose is to help you obtain the knowledge necessary to study at this institute. Russian students don't have this course of Introduction to Physics because in Russia the physics program at secondary school is very good and Russian students know physics very good. Those who are interested in physics, they can solve complicated problems, and when they come here to study at this institute, at this university, they are already on the necessary level of knowledge. But that's not the case with the students originating from different countries. In different countries, levels of education are different. So this course of Introduction to Physics will, first of all, we will repeat basic laws of physics which are usually studied at school. at secondary school, and then we will solve many problems to demonstrate what should be the level of skills of a student in solving complicated problems. You will see what should be your level of skill. Actually, in this university, we study physics and mathematics at the highest possible level. At the highest level of complexity, we study physics and mathematics very close to the modern scientific level. So the requirements are very high for the students. You are required to know a lot. You are required to have skills, good skills in solving complicated problems in physics and mathematics. So the purpose of this introduction to physics course will be to show you what should be your level so that you could work and improve and advance your level and improve your knowledge and improve your skills. We will have 2 classes every week. This class on Tuesday and another one on Friday, which will be held in the big physics laboratory, big physics audience. That is class number 500 on the opposite side of this corridor. 500, number 500. There is a large audience where a large classroom where we can demonstrate different experiments and demonstrational experiments in physics. So 2 classes every week, and in the middle of the semester you will have a mid-semester written test, and also you will have to solve a lot of problems by yourself. And today I will send you a link to materials to theoretical courses which you must study, and a link to a collection of problems in physics which you must solve. So I will send you a link later today, and you will see the textbooks in physics in English that you will have to study. The main textbook for you will be a 3-volume course of physics, a 3-volume course of elementary physics by Landsberg. Landsberg is a Russian academician who created this course for advanced school children, advanced school students here in Russia. A 3-volume course of comprehensive physics on elementary level, which explains everything from the very beginning. So that will be the main textbook for you. And also you will see, you will find there a collection of problems by Bukhovtsov, also a translation from Russian. And this collection of problems contains a lot of complicated problems, and you will have to solve all of them according to the program which I will send to you. You will see the number of problems which you have to solve every week, about 10 problems every week. Some of them we will solve here. Some of them, solution of some problems we will discuss here in the classroom, but not all of them. You will have to solve many problems by yourself, based on the theoretical material and on the formulas which you will find in the Landsberg course of elementary physics. We will not have the possibility to discuss everything here. We will not have enough time to discuss all the laws and all the formulas here. Many material, a lot of formulas you will have to learn by yourself. So your individual study and individual efforts will be very important for your success. Okay, after so many introductory words, let's start with kinematics, which is the simplest chapter in physics, probably one of the simplest. What is kinematics? Kinematics is a science which aims to describe the movement of bodies. Just the movement, without any consideration of the cause. Kinematics does not consider what is behind the movement, what causes the bodies to move. The causes of movement is called, the science which studies the cause of movement is called dynamics. And you know, the cause of movement is a force. Forces, accelerations are studied by Newtonian mechanics. So kinematics is not interested in the cause of movement. It's interested only in description of movement. So how to describe a movement of a body? First of all, we must consider the simplest body, which is called a material point. Material point is such a body whose dimension is very small compared to the scope of motion, compared to the scope of movement. So a material point may be a motor vehicle. If we consider the motion of a motor vehicle along a large distance, if a motor vehicle moves at many kilometers or hundreds of kilometers, then the motor vehicle itself may be considered as a material point. The planet Earth may be considered as a material point if we study the movement of Earth along its orbit around the Sun, because the orbit diameter is much larger than the dimension, the diameter of our planet. Any star, like our Sun, may be considered a material point if we consider the motion of star in a galaxy, along with billions of other stars. Every star may be considered a material point, regardless of the fact that the star is very large compared to the planet, and very, very large compared to any object on the surface of our planet. But nevertheless, the star may be considered a material point. Even the galaxy itself may be considered a material point if you study the movement of galaxy between billions of other galaxies in the universe. So a material point is any object whose dimension is small compared with the scope of its motion. So we consider material point, and how can we describe its movement? In order to describe the movement, we have somehow to define the position of the body. And in order to define a position, we must choose a reference frame, and we must measure the distance of this point from the beginning, from the origin, which has a zero distance from itself. Then we must choose some unit of length. Unit of length, like 1 meter, for example. So this is 1 meter, and 2 meters, and 3 meters, etc., etc. And so if we can count how many meters this point is away from the origin, then we will know the position of this point along the axis, which can be designated as x-axis. So in order to measure the position of material point, we must introduce some unit of length, like 1 meter, and we must count how many meters this point is away from the origin. The origin is any arbitrary point. So if this is the road, and this is the motor vehicle which moves along the road, then we must choose some point on the road, for example, some stone besides the road, and we must measure the distances from the stone. And to measure the distance, we must use the unit of length, like 1 meter. How do people define a unit of length? What is the unit? What is the 1 meter by definition? What is it? Do you know what is the definition of 1 meter? What is it? How to explain? How much is it? 1 meter. So the definition of 1 meter must be universal. It means that the definition must be applicable in any laboratory in any country. So that in any laboratory in any country, people could reproduce the length of 1 meter somehow. There should be a procedure to reproduce this length. And it should be exactly the same in every laboratory in different countries. So we have to devise such a procedure. We have to define 1 meter according to some certain procedure. Well, people changed this definition many times during the last 2 centuries. During the last 200 years, the definition of meter was changed. Well, maybe 3 or 4 times, I don't remember. First, people measured 1 meter as certain part of the distance from the North Pole to the great circle, to the equator of our planet. So the definition from the North Pole to the equator is the same for any country in the world, for any laboratory. And if we define the procedure to measure this distance using astronomical tools, and we define the meter as certain part of this distance, then the meter will be the same for all people on the planet. That was the first definition of meter. Then people understood that this definition is not very precise. It does not provide a good accuracy because the planet Earth is not an ideal sphere. It's something more complicated shape of our planet. It's not an ideal sphere. And besides, well, the procedure is not very precise. It cannot provide a good accuracy. Then people devised a different procedure. They produced a bar, a metal bar, with 1 liter length of 1 meter length, and then they made many copies of this bar and sent these copies to different laboratories in different countries of the planet, and that was the prototype. That initial bar was a prototype of 1 meter, and all the copies of this bar were the copies of 1 meter, so they were equal to 1 meter, and in every laboratory people could use this unit length to produce all the rulers and all the means to measure distance based on this 1 single meter. So that was another procedure to measure, to define a meter. But again, this procedure turned out to be much more accurate. It provided better result and smaller errors in producing 1 meter in any country. But this procedure was later changed to a better procedure, which produced even better result with smaller errors and with higher accuracy. And this new procedure, procedure number 3, was based on optical measurements, of interference measurements of the wavelength of some optical transition in certain element in krypton, a certain optical transition in red-yellow line, and using interferometer you could measure the wavelength of this optical radiation, and a certain number of such wavelengths was adopted to be equal to 1 meter. So that was a third procedure to provide the length of 1 meter. And now recently people have come to procedure number 4, which is even more intricate and more complicated, but it gives better result in terms of accuracy. And the modern procedure based on the time of travel of speed of the speed of light and travel of light. Yeah, the modern procedure based on the time interval required for the light to travel 1 meter. This modern procedure differs a little bit. It's also based on optical instruments, but it differs from the measurement of number of wavelengths, and it produces the highest possible accuracy in defining the unit of length. So actually there are many different procedures to define the length of 1 meter. Different procedures are characterized by different accuracy. And the modern procedure provides the best accuracy ever. But if you take the procedure of 19th century procedure, which was based on the length of the metal bar equal to 1 meter, that will provide, well, good accuracy for most of engineering measurements. Most of engineering measurements, you will just compare the length of metal bar with the prototype meter, and that provided, well, good measurement, good accuracy, which can be applied in many engineering and scientific measurements. So if you have measured the number of unit length here, this number of meters will define the distance of this point from the origin, and this distance may be denoted by x. If the body moves, then the coordinate x, this is called the coordinate, will be a function of time. It means that the coordinate will be different at different moments in time. For example, at the beginning of measurement, at the time moment t0, the body was here at this coordinate, and then at time moment t, the body came in this point. And so if the body moves, then the coordinate changes in time. The coordinate x changes in time. It's a function of time. It can be any function. We can draw this function x as a function of time. It can be any function. Five minutes interval. Okay? Okay. After this short interval, I would like to ask you a question. So any function of time may represent the actual dependence of coordinate, of a material point coordinate versus time. Let's draw another function. For example, this one. Can it be a real motion? Can this graph represent a real movement of a particle? Why not? Yes, it cannot go back in time. So at this particular time, according to the graph, the particle moved here to a previous time moment. So it went back in time, but it's impossible. It's impossible to go back in time and the particle will meet itself here at this point. It's impossible to meet oneself in the past. It's impossible. So such a curve is impossible. Где тут у нас? Okay. So we will consider only a real movement of particles, and as the first example, I would like to consider such a movement which will be described by a straight line. So this point is considered to be 0. The time equals 0 at this point. It means that we started our time counter at this moment of time, and we measure time starting from this moment. And also the particle coordinate at this point is 0, so we measure the coordinate of particles starting from this origin. And that will be the initial coordinate of a particle. Again, it's very small, right? It's very small. Let me show it larger. Is that okay? That x0 seems to be larger. Okay, so x0 is the initial position of the particle, and at some time t, the position of the particle will be x. That will be x of t. By definition, the quantity called speed is the change of coordinate divided by the time interval during which the coordinate has changed. By definition. So this is not the physics law. This is just the definition of the speed. What is delta x? Delta x is the change of coordinate. So this is the current coordinate x minus the initial coordinate x0. And what is delta t? It's current time minus the initial time. Initial time in general may not necessarily be 0, but in our particular case, initial time is 0. In our particular case. But in general case, the initial time moment should not necessarily coincide with 0. It may be any number of seconds, or minutes, or hours. From this definition of speed, we can easily obtain this quantity x coordinate as a function of time, which will be equal, if the initial time is 0, if t0 equals 0, so this is absent here, then the x coordinate will be equal to x0 plus the speed multiplied by time. This is the consequence of the definition of speed. And if the speed of the material point is constant, then that equation will describe the movement of a material point with constant velocity, constant speed. What is the difference between speed and velocity? Do you know? What's the difference between speed and velocity? Yes, speed is scalar quantity and velocity is vector. You know that the speed is vector, actually. We will discuss it a little bit later. And so when we consider the speed as having a direction in space, then we call it velocity, underlining that this is a vector. But when we are not interested in the direction, but we are interested only in the distance traveled by a particle, then we call the velocity as speed, to underline that this is a scalar quantity. So that will be the equation of motion, of movement, particle movement at constant velocity, at constant speed. In this equation, speed is constant. Okay. So where is delta x on this graph? Delta x is x minus x0. So this section equals delta x. And this section can also be shown here. This is delta x. And where is delta t on this graph? Delta t is this section, delta t. So if we consider this right angle triangle, then this triangle will have two legs, this leg, vertical leg, and horizontal leg. And the speed, by definition, is delta x divided by delta t. So the speed will be the vertical leg divided by the length of horizontal leg. And that, by definition, is tangent of this angle alpha. So the speed turns out to be equal to tangent of angle alpha, because tangent, by definition, is the opposite leg divided by adjacent leg. Okay. Now let's consider a movement of different material point, and this different movement will be described by a different graph. For example, this will be the line describing the movement of a second material point. What can you say about this movement? What is the speed of this movement, first of all? So here the speed is tangent alpha, which is just delta x divided by delta t. And that will be a positive number. What about the speed, the sign of the speed here for such a graph? It will be negative, certainly, because here delta x will be negative x minus negative 0, but x0 is smaller than x in modulus, and therefore this section will be negative. Negative number divided by delta t will give you a negative speed. By the way, this angle, for example, let's denote it by beta, will also be negative, and the tangent will be negative. This angle. So here the velocity or the speed is positive, and for such motion the speed is negative. What if the speed is equal to 0? How can we show such a movement? This is also a particular case of movement when the speed is 0. How can we show it on this graph? If the speed is 0, then the material point is at rest this point. And at rest, it means that time goes on, but the position doesn't change. And on this graph, it will be a horizontal line. Horizontal line means that the speed is 0. And the tangent of this angle will be 0. Okay. That's all there is to say about the movement at constant speed. It's very simple. Let's now consider a situation when a speed is changing. If the speed is changing, then we say that the material point moves at some acceleration. It has some acceleration. And by definition, acceleration is the change in speed divided by the time interval during which this change took place. So if we draw a graph of speed versus time, so there may be initial speed, v0, at some initial time, t0, and the speed may change somehow, so that time moment t, there will be some speed v, final speed of material point. The speed changes with time. As time goes on, the speed changes. In this particular case, the speed increases. And by definition, the acceleration of such material point is delta v divided by delta t. What is delta v? It's easy to see that delta v is final velocity minus final speed minus initial speed, v minus v0. So this is delta v. And what is delta t? It equals t minus t0. The time moment t minus time moment t0. From this definition, we can easily obtain the velocity or the speed v. Again, this will be very simple if the initial moment of time is accepted to be 0. Well, it doesn't work. So we try another pen. If the initial moment of time is 0, then if t0 is equal to 0, then the speed v will be equal to v0, this one, plus acceleration times t. That will define the speed as a function of time, provided acceleration is constant. The speed as a function of time. That equation will give you this curve. The speed as a function of time. If a material point moves at constant acceleration, then this motion is called uniformly accelerated. This is a uniform motion, uniformly accelerated movement of a particle, right? Uniform motion with uniform acceleration. Well, it looks very similar to the formula we have written before for the coordinate of a material point which moves at constant speed. And now we have not the coordinate but the velocity of a material point which moves at constant acceleration. These two formulas are very similar because in this particular case the velocity or the speed was constant, and in this case the acceleration is constant. That will provide the dependence on time of the body's coordinate, and in this case the dependence on time of the body's speed. Okay. If we turn to this graph, what will be the distance traveled by the particle? So this is the time, and this is the coordinate, and the distance traveled by the particle is the coordinate difference, that is x minus x0. That will be the distance covered by the particle. If we go to this graph where we show the speed versus time, how can we find the distance traveled by the particle on this graph? Suppose the speed was constant. Suppose the speed is not changing in time. Then the speed, the constant speed, will be depicted as the horizontal line here. That is the movement at constant speed. And if the speed is constant, then we know that the distance traveled by the body, delta x, is the speed times delta t. What is speed times delta t? If the speed is constant, that is v0, then v0, which is this vertical section, multiplied by delta t, which is this section, this product of v0 times delta t will give you the area of this figure. So the distance traveled by the particle, delta x, will be equal to this area on the graph. It depends on time. The larger the time, the larger the distance. And if we choose a very small time interval, very small time interval, then the distance traveled by the point during this small time interval will be given by the area of this figure. And if the particle speed changes from this value to another value, then again the distance traveled will be given by the area. So if the velocity changes, anyway, the distance covered by the particle will be given by the area under this curve. So if I consider the total area of this geometrical figure, then the total area under this line, which shows the dependence of velocity versus time, the total area of this figure will give you the distance covered by the material point. So how do you call this geometrical figure? It's a trapezoid, right? It's a trapezoid. In order to find the area of the trapezoid, what do we do? In order to find the area, I will denote this area by F. So in order to find the area, what do we have to do? We must take one base and another base and find the middle line, find the length of the middle line, which will be the first base V0 plus the second base, which is V, divided by 2. That will be the length of the middle line in this trapezoid. And the length of the middle line should be multiplied by the height, that is the distance between the two bases, which is just t. We suppose that t0 is taken as 0, as the beginning of time in our experiment. We start measuring time at this point. So t0 equals 0. Therefore, I can denote the distance between two bases, the distance between these 2 points, just like t. Otherwise, I should have written t minus t0 if it were non-zero. Okay, so this is the area of this figure, and we have already come to conclusion that this area should be equal to distance traveled by the particle, even if the velocity of the particle changes from v0 to v. The area under this graph will show you the distance covered by the particle. Okay, if this is the distance, then we can use some simple algebraic transformations. I will leave v0 where it is, and instead of v, I will use this expression. Instead of v, the speed of the particle at time moment t, equals this expression. So that will be v0 plus a t divided by 2 and multiplied by t. After such simple algebraic transformations, we will have 2v0 divided by 2, which means just v0 multiplied by t plus a t squared divided by 2. That's it. That simple formula gives you the distance traveled by a particle which initially had the speed v0 and constant acceleration a. And in time interval t, it travels such distance. How did we come to this formula? First step, we understood that the distance equals the area under the curve, describing the movement of the particle. But this curve describes the velocity versus time function. We have to consider velocity versus time. And so if velocity is shown along the vertical axis and time is shown along horizontal axis, then in this particular case, the area under the curve will equal distance, will be equal to distance traveled by the particle. And after understanding that the distance is related to the area, we can easily calculate distance by just using geometrical considerations to calculate the area of this trapezoid. And trapezoid area is the middle line, which is half the sum of two bases times the height, which is the distance between the two bases of the trapezoid. So we use geometrical considerations here to calculate the area, and we know that the area is the distance. And by the way, it's denoted by the same letter S. S is distance and S is the area. So in this way, we have arrived at this simple formula, which gives you the distance traveled by a uniformly accelerated particle which moves at acceleration a, provided the initial velocity was v, the initial speed was v0. My purpose is not only to repeat the simple formulas of kinematics, but also to repeat with you other simple issues like transformation of units, for example. Transformation of units. Let's consider a simple example on transformation. Suppose a body moves at the speed of 10 meters per second. How many kilometers per hour will that be? The speed can be measured in kilometers per hour, right? But if I have such a figure of 10 meters per second, how many kilometers per hour will that be? 10 meters per second, we have to transform it into different units. So this is 10. What about 1 meter? 1 meter is which part of a kilometer? It's 1,000th part of a kilometer. Because 1,000 meters, a kilometer equals to 1,000 meters. So 1 meter is 10 to the minus 3 of kilometer. And here we have 1 second, and we have to transform it into an hour. So how many seconds are in 1 hour? 3,600. We know that 1 hour is 3,600 seconds. So 1 second, therefore, is 1 divided by 3,600. That is the part of an hour. So the relationship between 1 second and 1 hour is given by such fraction. We have to use it here, because here we had 1 second, and we must express it using hours. So that will be 1 divided by 3,600 hours. Okay. So that will give you what? 10 remains on its place. 1,000 will go to denominator. That is 10 to the minus 3. That will be 1,000 in denominator. And 1 divided by 3,600 will be in the numerator. And that will be the number of kilometers per hour. So the only thing remaining is to cancel the zeros, that is to divide by 10, to divide by 10, to divide by 100. And what remains here? 36 kilometers per hour. 36 kilometers per hour. Right? That's an example of transformation of units. If you have a velocity of 10 meters per second, that's equal to 36 kilometers per hour. And vice versa, if a motor vehicle moves at 36 kilometers per hour, it makes 10 meters every second. So if the motor vehicle makes 72 kilometers per hour, how many meters per second? If the velocity is, if the speed of a motor vehicle is 72 kilometers per hour, how many meters per second does it make? If it's 72 kilometers per hour, then how many meters per second? Twice as much, the 20 meters per second. That's usual velocity of motor vehicle, something like that. 15, 20 to 30 meters per second. That's what they do on the road. Okay. Any questions about this transformation unit? Is it clear? This one. This. Okay. If you divide by 1 over, let's do it in this way, in algebraic way. If I consider A divided by 1 divided by B, what is it algebraically? I have to multiply both the numerator and denominator by B. That will not change the fraction, and that will give you AB divided by B divided by B. I multiplied this one by B and this one by B, right? So here we have unity, and that will be AB. So if I divide anything by such a fraction, then B goes to the numerator. The same was here. We divided by 3,600, which went to the numerator. Just simple algebra. Any more questions? Everything's clear here? Okay. So, returning to our formulas for uniformly accelerated movement. Let's suppose that the initial velocity here was 0. So if the initial velocity is 0, then the distance traveled by a material point will be given by this term. It will be a t squared divided by 2. It's good that you asked this question, and I recall that it's possible to multiply the numerator and denominator by the same number. And so here we multiply the numerator and denominator by a. We will obtain a squared, t squared, and multiplying the denominator we obtain 2a. Anything changed? Nothing changed. This formula is the same. It did not change because we can cancel by a and obtain the same expression. Nothing changed. But now it's obvious that at equals the velocity in case v0 is absent here. If v0 equals 0, then at equals the speed. So at is the speed. That will be v squared, a squared, t squared, divided by 2a. That's another simple formula to find the distance traveled by a particle. If you know the constant acceleration and if you know the final speed, then you can calculate the distance if the initial speed was 0. Oh. Okay. So let's consider this formula again. The distance is proportional to t squared if the initial velocity was 0. I will put it this way. Distance is a t squared if the initial velocity, if v0 is 0. If the initial velocity is 0, then the first term is absent, and the distance is defined by the second term, at squared over 2. Can we show the graph of this function, that is s, distance as a function of time? Yes, sure, we can show the graph of this function. This is a quadratic dependence. Distance is quadratically depending on time. This is a parabola, so that will be something like this. The distance traveled by a point particle as a function of time. It's proportional to time squared. That's it. That's the point, the time origin. At this moment of time, we started measuring time intervals, and that along the vertical axis we show the distance s, which is proportional to t squared. So at some moment t1, the position will be s1, the position of the particle. At some other moment in time, which is t2, the position will be s2, right? What is s1? The distance covered by time interval t1. According to this formula, s1 is a t1 squared divided by 2. Also s2, according to the same formula, is a t2 squared divided by 2. S2 is the distance traveled during time interval from 0 to t2. From these two formulas, we can easily find the distance traveled during time interval t2 minus t1. So this distance, I will denote it as d. Something again happens with this pen. It doesn't work properly. I will denote it as d. So distance d traveled during time interval t2 minus t1, during this time interval, will be defined as distance s2 from the 0 point minus s1. S2 minus s1 will be given as a t2 squared divided by 2 minus a t1 squared divided by 2. So the difference between these two distances, s2 minus s1, s2 minus s1, will give you the distance covered, the distance traveled by the body during the time interval t2 minus t1. That's clear. The simple formulas written here show you that this distance can be expressed as a divided by 2 t2 squared minus t1 squared. That's another formula. Also, if we multiply the numerator and denominator by a here, we will obtain a t2 squared minus a t1 squared divided by 2a, because I multiplied both the numerator and denominator by a. And what is a t2? Acceleration a multiplied by time interval equals the velocity, provided the initial velocity was 0. So on this graph, the initial velocity was 0, the initial position, and the initial velocity was 0. So the initial velocity v0 is absent here, and a squared t squared will be equal to v squared. That will give us a2. This is the second time moment, t2. That will give us the velocity at the time moment t2 squared minus the velocity at the time moment t1, v1 squared divided by 2a. That's another useful formula to calculate the distance traveled by a uniformly accelerated material point. If you have a uniformly accelerated, that is, moving at constant acceleration, material point moving at constant acceleration a, and initially it had velocity v1, and finally it had velocity v2, then it traveled this distance d between these two moments of time in this time interval. Another useful formula which allows one to calculate the distance covered by a body if you know the initial velocity and the final velocity and you know the acceleration. Then you can find the distance. Okay, we are very close to the end of this lecture. Later today, I will send you a link to studying material, and you will see everything you have to learn, everything you have to solve. So, see you on Friday. Goodbye.